Hello. Today we're going to be taking a look at average value. Now, you're going to notice some similarities between average value and MVT today, hopefully. Now, to begin with, let's start off with the function here between A and B and f of A, f of B. Okay, so we're going to draw our secant line here, which we'll come back to in just a second. Now, from earlier this year, we talked about how we get slope, right? Remember, slope is change in y over change in x. So if I were to kind of cross multiply this one, I would get delta y, change in y, equals the slope times my change in x. And we had a special word for this. This was called our differential. Okay, it was called our differential here. And we did a lot of things we can do with this one. But what I want to focus on is just this part right here. Delta y is my change in my y values. But if I look at my graph, that's just going to be this f of b minus f of a equals my slope. Now, what is delta x? Well, that is our b minus a. If I solve for m, we're going to get the slope of our secant line, which is right here. This is my secant line. And to get the slope of a secant line is just f of b minus f of a over b minus a. We called that average rate of change earlier this year, and that should look very familiar to us. What I want to pay focus attention is the top part, this f of b minus f of a. Now, we know from the FTC, the fundamental theorem of calculus, that the antiderivative, the area under the derivative curve from a to b, is f of b minus f of a. Take a look. The difference in my values is the area under my derivative curve, is the area. So I could rewrite my slope, which for us finds an average value. Because that's really what slope is. Slope is just an average value between 2 points. So we can rewrite our average value as the following. The antiderivative of a to b of f of prime of x dx over b minus a. And that's how we get our average value function. Now, we write it more this way. Average value is the following. We don't like this, it looks complicated, so we write it this way. It's going to be your favorite function. So favorite function is the following. 1 over b minus a. And we're going to use f of x instead of using f prime of x, although remember, anything inside the integrand is considered a derivative, so we don't have to, it's implied as a derivative, so we don't always have to write it out so. And this is what we call our average value. What this will find is the average value of the function over time. And we're going to take a look at a couple of examples right here real quickly as well. So, to begin with, let's take a look at the function f of x equals x minus 2 squared on the interval 2 to 5. And I want to find the average value. Now, if I were to graph this function from 2 to 5, it starts, let's do x minus 3. If I graph it, very easy to do. If I plug in the 2, we're going to get 1. And if I plug in the 5, we're going to get 4, and I get my function here. And I can find the area underneath that curve. We'll talk about that in a second here. But what we're looking for is the average value that this graph takes on between 2 and 5. So we have a formula for that. Now we know what average value really is. Remember, an average is really just your total number of scores, the total scores. If you total all your scores, and then you divide it by the number of scores. Kind of like taking a test, right? If you had an 80 and a 90 on a test, you would add them, divide it by 2 to get an 85. It's an average. It's the same way. So I got to get my sum of all my total scores. And to do that, that's what this finds, the integral finds. So my average value, very simple, becomes 1 over, I just use my formula, 5 minus 2 times the antiderivative of 2 to 5 of my integral. x minus 3 squared dx. Now I'm going to use u substitution here. U is x minus 3, du is just dx. So this becomes 1 over 3, and this becomes u squared du. Now, I will change my domain. When x is 2, u is negative 1. When x is 5, u is 2. So when I integrate this, I get 1/3, and this is going to go from negative 1 to 2, u cubed over 3. And when I write out my answer, I'm going to get this. This becomes 8 over 3 minus a negative 1/3. And what do I get? This becomes 9/3, or 3. So, what is this right here? Well, this is the sum of all my scores. That's the area, the sum of all my scores. That's the area under my curve. What's the 1/3? It's like the number of scores that we have. So what I do, I multiply them together, and I get 1. This is my average value. Now, in terms of the problem, it's kind of like this. It's the average height of my function. That's how we can kind of look at it. This is the average height of the function. In other words, I can graph that on here. This is the average height of my graph. Now, the next part that sometimes they'll ask us is, where does the average value equal the function? In other words, where does my fave equal the value of the function, f of x? Well, that's easy to do. 1 equals x minus 3 squared. If I solve it, I get x minus 3 equals plus or minus 1. So in this case, I get 2 or 4. So that's saying at 2 and 4, the value is the same. Now, but what does an average value mean? Well, it says I can draw a rectangle at y equals 1 from 2 to 5 that has the exact same area as the entire function itself, because that's how averages work. So I can draw a rectangle at y equals 1 from 2 to 5, and that'll give me the same exact area underneath my graph as well. And that's how the average value works. In terms of like more of a real world situation, let's take a look here. We have the velocity of a bike, and it's given on the table below. We use the data to estimate the average velocity for the first 9 seconds. So I want average velocity. Well, I know from physics that velocity is your change in distance over your change in time. Well, the problem is they didn't give me distance. What did they give me? Velocity. Well, we know from calculus to get distance, we're going to look at the antiderivative of velocity, dt. And we want the first 9 seconds, so we go from 0 to 9. And this is basically how average value works. I divide that by my change in time, which in this case 9 minus 0. And if you notice, this is my average value formula right there. So change in distance over change in time. Now, I just have to remember, how do I get this change in distance? It's an area problem. Now, they didn't tell me, so I get to make a choice, okay? So I'm going to choose a left Riemann sum here to get the area. In other words, that's going to give me the area from 0 to 9 of my velocity curve. Now, if I use my Riemann sum, I'm going to go 0, 3, 5, 7, 9. Left Riemann sum, I'm going to use a 5. At 3, the height was 9. At 5, it was 11. And then 13. I'm looking for the area underneath here, so it's going to be 3 by 5 plus 2 by 9 plus 2 by 11 plus 2 by 13. And I'm going to calculate that, okay? So if I turn on the calculator here, if I type it in, that's 15 plus 18 plus 22 plus 26, and we get 81. Now, we haven't talked about units yet, so let's take a look here. V of t, in terms of units, this was meters per second. The dt is in seconds, so those cancel. And look, we do get meters. So we traveled 81 meters in those 9 seconds. Now, but we're not done, because remember, I had divided by my time. So what I really wanted was this. I want the antiderivative of 0 to 9, v of t dt, over 9 minus 0. And if I think of it in terms of units, remember, the top here is meters, the bottom's going to be in seconds, which will give me meters per second, an average velocity. So let's go ahead and calculate that. Well, we know that this one was already 81 meters, and this is 9 seconds, so we get an average velocity of 9 meters per second. Okay? And that's how average value works. All right, so try a few on your homework, and good luck with this. If you have any questions, feel free to ask.